a long corridor of dialog boxes or something. But, are you folks, is someone able to connect just to verify that? Okay, great. Yeah. So within this class, we're going to be hitting on a number of topics. The first one will be focused around an exercise that I asked you to pursue. This exercise requested that you undertake a process of creating an operator, an operator that operates on functions and returns a function. And that operator is the differentiation operator in a numeric sense. So here I had asked you to create a function that, given a unary operator that it takes in, and a value of epsilon, a very small differential value, it serves to differentiate that unary operator around a certain point, which we call x0. Okay, and x0 was specified to be specified separately than the original function at epsilon. The idea being that by separating it out like that, by having it specified separately from the function itself and the epsilon to achieve, we could have flexibility. And the flexibility would be, specifically, we could apply the derivative operator that we got back to different x0s. Okay, so the idea here is we wanted to be able to differentiate this function with a fixed epsilon and then apply it to different x0s at different times. So sometimes we could apply it at x0 equals 1, sometimes x0 equals 2, sometimes at other locations. Okay, and we might apply it at thousands of different locations. X0 represents the point at which we want to detect this. We want to report the slope of this function that we passed in, right? This fn unary, it's a function of x. You can think of it as x, say, and we want to evaluate its slope, its derivative, at different values of x. That's x0. Okay. So I asked you to create an operator like that, and I created solutions to show you one way of doing it. And in fact, I show you here 2 ways of doing it. One of them is more, perhaps more clear, more basic in its implementation. The other makes use of some of Scala's niceties in the form of multiple parameter lists. And we'll walk through both those options. So the first one, the one that's kind of simpler here in terms of the operation or the constructs that it uses, is this derivative operator. So this takes a function from values to values, in this case from x to the value of the function at x, and it takes in an epsilon, a small differential value. And having done that, it returns a function. And this is the function that it returns right here. So that function takes an argument, which is the value of x at which to evaluate the derivative, x0. And it computes the derivative in a numeric sense, where, again, this derivative is computed according to principles of calculus by taking the difference in the value of the function on the numerator and divide it by the difference in the value of x, the variable with respect to which we're differentiating the function x in the denominator. And by definition, epsilon is kind of the small distance over which we move x to judge the slope. And so we're changing x, the variable over which we're differentiating the function, df dx. So it's x. We're changing that by epsilon. We're comparing the value at x0 and at x0 plus epsilon, right? So that's the difference between them of epsilon. You subtract these two and you get epsilon. In the numerator, we have this. That's the quantity being divided. And so that's exactly what we have in place here. This is the numerator, right? The unary function evaluated at x plus epsilon, x0 plus epsilon minus that function applied at x0, right? And we divide it by epsilon. All right. So so in short, with this version of the function using simpler constructs, we take in the function to be evaluated in epsilon, and we return back a function of x, or of x0, we call it here. Takes in an x0, and it evaluates the derivative of the specified function using that epsilon at x0. Does that make sense? Mm-hmm. Yeah. So this is a higher order function. Higher order functions are functions that either take a function as an argument, return a function as a return value, or do both. Okay. You might argue in imperative language it's also something that can assign a function to some other place. In this case, it does both, right? Here, we're taking a function as an argument, the function which we wish to differentiate, whose differential we wish to take, and we're returning a function as a return value. These sort of higher level functions will be, higher order functions will be very common in Scala as we use it in Spark. There's user-defined functions, which we'll be using there, and we can achieve a great deal of flexibility with that. Here, we could take the derivative of any unary function very straightforwardly. It's quite orthogonal. The operator exists regardless of the function whose derivative we want to take. We want to apply it to a square operator, for example, right here. We can do so by just passing in a square function, right? That's what's going on here. We want to apply it to a linear operator, like doubling the value of x. We can pass it in and get back the derivative of that function. We want to pass it, if we want to differentiate an exponential operator, we can pass it in and we get back a function that's the corresponding differential. This is an operator, operates on functions. It takes in a function as an argument and returns back a function. All right. And the function it returns back knows how to apply the derivative of the function, evaluate the derivative of the function at different particular points, right? So that's what these different values are here. It's a straightforward idea that's very powerful. I will note that all of this, like the existence of currying in general, depends upon closures. Anyone remember from last time what a closure is? What's a closure?
It's a function.
It's a function.
It's a variable.
Yes.
Which is varies outside of function. Okay,
good. Good. It has a free variable and it remembers that free variable. It remembers the value. In fact, in this case, for this sort of language, you can actually modify that value if you want to. So it actually remembers the location associated with that value. But the point is it's wrapped up with all the information it needs to do its job. So when I said the derivative operator returns a function, that was true to a point, but actually it returns a closure. It returns a function that knows everything it needs to do its job. And what it needs to do its job in this case are in fact three things. Well, actually two things that it remembers from here that are free variables. The two things are x0 and epsilon. It needs to remember their values, right? By contrast, x0 is is something that's directly specified to this function, so we don't have to remember it. It gets told to us at the time we apply the function. But these other two are free variables we need to remember, x0 and epsilon. So when we call this thing with take the derivative of 2 times x at epsilon being 1e 10 to the minus third, we get back a function that remembers that particular value of the unary function and of x0, right? But excuse me, not x0, unary function and epsilon. X0 is provided when this function is invoked, like here. That's when x0 is provided. So the two things it has to remember, not sure I said them properly, are unary function. The closure needs to remember the unary function and remember epsilon. Those are the two things specified outside of this function that it returns, right? So all this depends on closures. The fact that diff of x knows how to differentiate a sort of identity function, how diff of x squares knows how to differentiate the square function, quadratic function, diff of x knows how to differentiate exponential function. The fact that it remembers this is a reflection of closures. It's a closure that allows it to remember this. And pairing functions as arguments with closures is incomparably more powerful than just being able to pass functions in and of themselves. An example of that would be in C, where we pass function pointers. And function pointers are all great, and you can use them to strong effect, but closures are much more powerful because they remember all the information to do the job, and they can really clean up your program because you don't have to carry around information with them. And when you apply them, you don't have to specify separately all this information they need. Rather, with closures, they'll, at the point they're created, like we created this function, from then on, it remembers all the information it needs to do its job. And that's really valuable. It's really valuable. We could often then forget. We just don't bother keeping track anymore that we told it to take a derivative of a square function with epsilon being 10 to the minus third, because it remembers it for us. It goes off and remembers it, right? And from then on, it carries on the information to do its job. And this is very, very useful. For example, maybe you want to set up an event handler, but the event handler, when it gets an event, it needs to do some specific thing that requires some knowledge of what to do. And what you could do is you can create an event handler that remembers all the information it needs to do its job. So when it gets an event, it searches for a certain string in a certain location with these case options or whatever. And from then on, all it has to do is process the events, and it knows all the information it requires to do its job, right? Makes sense. Okay, so then I asked you further, as I recall, to test it out by applying these things on a vector. And can you see my screen on live events? Okay. So that's what I did. I used this tabulate, vector tabulate here. Now, Scala collections have an admirably wide repertoire of different options you can use with them. So there's something called iterate, there's something called tabulate, there's something called fill, which we've used before, right? There's various ways of filling up a vector, and here we're using this tabulation, and tabulation basically allows you to pass in, first of all, something that tells how big a thing you want to create, and secondly, a function that is provided the index that you're initializing. In this case, we call it I. So if we're initializing the first element, that's 0. Second element, that's 1. And it tells us what to put there, right? So you know, a little example here would be, here we go, boom, and okay, we'll just do it 10, fine. And so here it's -1 plus the index, right? So the first one is -1, the second one is 0, because it's 1 plus -1. Etc. Or, for example, we could square the index, right? But there we go, right? And we'll get a set of squares, 0, 1, 4, 9, 16, and all that sort of good stuff, right? Okay. So, ladies and gentlemen, tabulate is a useful way of producing things when you want it to depend on index. Iterate allows us to apply things by contrast in a sort of successively recursive way to iterate a certain function a certain number of times. Okay, looks good. Okay, so that's one way that we could engage in it. Here's another way. We can create a stepping here, which basically takes this range that's incremented by 0.25 and converts it to a vector, right? In any case, we do this, and then to apply our operator at each point along that vector, to apply our differentiated operator, we can just map it onto this, right? We map it so that for each element of vectest, this differentiated function is evaluated at that point, right? So for example, we have vectest here, and I'll apply it to the differential of the square operator. Okay, let me go define it here. Here we go. Boom, boom, boom. We'll define it and we'll apply it. Mumble. Oh, sorry, I didn't actually evaluate my differentiator there. There we go, and here we go. Boom. Okay, so here we've applied it to two particular things. This is where we create our differential. We apply the derivative operator to this function. We get back a function, diff of x squared, that we apply to 1, and it tells us it's 2 at that point, right? Because symbolically, the differential of x squared is 2 times x. And so this is x, and so 2 times it will be 2. This is x, 2 times it will be 4. And if we want to apply that to our vectest, here we go. Boom. There we go. And it's applying it at each element of vectest. The first one is -1, so twice it is -2, etc. Alternatively, we could apply it at here. We'll have the differentiation of the exponent operator. Oh, import scala.math. Import. Oh man. Scala. Now I'm in trouble. Okay. Okay. Yes. Okay. Happy. So the differentiation of an exponent, does anyone remember? Yes. Yes, it's awesome. It's the eigenfunction of the derivative operator. You pass it in, you get the same thing back, and it's beautiful. Take my word for it if you don't see it. Happy. Okay, so ladies and gentlemen, that was the take-home exercise. Any questions about this? So what I'm going to do is to therefore stop recording here, and I will have a brief conversation with Merlin, the magician, who stands